Okay, so I had to break the video up into two parts. Two reasons, technical issues in the last one, and I ended up right around here. And I just wanted to explain this little step even clearer. And before we go to the last bit of it, at least the conclusion of the video. So what I'm doing here again, just to go back over things, we took the integral of the first part, which was, and this is the result of the maximum part of the function, which we'll see right here up top. This would be the maximum, but the limits are from 0 to 1 over 1048, and this is the minimum part, and the limits are from 1 over 1048 to 1 over 524. So that's why we have two results here. This is for the max, this is for the min. And so the 1048 here is common to both parts. That's why it's distributed out, 1048 times 1, 1048 times minus 7/8. And so I just continue that here and the next part. But I just wanted to clear up that last bit for this part and just keep it simple. So the 1048 is multiplied here by this first term, and then also the 1048 is multiplied by the second term here. So it's going to be negative 1048 times 7/8 that we see here. 1048 times 7/8, negative 1048 times 7/8 that we have here. And I just keep the minus sign because I think in the last one I had the plus sign in there, which I just distributed seemingly in my head, but I just wanted you to see how that becomes positive, when we distribute this, but that part wasn't quite clear. So I just kept the minus signs here, the minus cosine n pi, and we see the minus cosine n pi here, and the plus cosine n pi over 2 plus cosine n pi over 2. And so now I'll be able to distribute it a little bit clearer to show you how I'm going to get the next result. So I just kept the signs and multiplied everything by 1048. Okay, so now just to continue to distribute the terms. As we can see, this entire part here, this is a numerator, and this is divided by 524 n pi. So as we can see for both of these terms, there's a 1048 over 524 n pi for both, 1048 over 524 n pi. So what I can do is distribute out a 2 over n pi, because 1048 divided by 524 is 2, and then that's going to be divided by n pi. So what I will have is 2 over n pi, and then I will just distribute the rest of the terms. So 2 over n pi minus so I think I'll just keep the brackets. That's going to be minus cosine n pi over 2 plus 1. And then since that 1048 goes away because it's been distributed over this 1048 over 524 n pi, so those terms are no longer there. They're been factored out as this 2 over n pi. So what I'm left with is a positive 7/8. So I'm just going to just write it here. So plus 7/8 cosine n pi. And then because it's minus minus, this is positive. Remember, 1048 divided by 524, 2 over n pi times this, 1048 over 524, 2 over n pi times this. That's why it's been factored out as a huge bracket. So maybe I should just do this here to denote that this is a distribution. The 2 over n pi has been factored out. So now it's going to be multiplied by this term here that we see up top, negative cosine n pi over 2 plus 1. And then this is minus minus, so it's going to be plus 7/8 over cosine n pi. And then this minus sign corresponds to this term here, so it's going to be negative 7/8 cosine n pi over 2. So negative 7/8 cosine n pi over 2. Now we can, and then again, this is a huge parentheses. Now we can just like break everything down, algebra. So this negative cosine n pi, that goes away because cosine pi over 2 is 0. And so we're just left with, let's see. Well, you know, obviously eventually that becomes 0. But I'm gonna, before I do that, I'm going to just combine like terms. And so I'll have my, let me just do this here. This is going to be negative cosine n pi over 2 minus 7/8 cosine n pi over 2. And that's going to be, of course, it's going to be added to these other two terms here, the 1 plus 7/8 cosine n pi. So once we, you know, do our factorization here, this just becomes negative 15/8 cosine n pi over 2. Because the understood 1 here, you factor the 8th to both sides, 8, 8. So it's going to be negative 8 minus 7 over 8. So minus 8 minus 7 is negative 15 over common denominator 8. Negative 15 over 8 cosine n pi over 2, the result of this. So now, Fourier series is one of those things where you really have to be careful, and they can get very long, but it's good for you. You know, it teaches you the discipline and the detail, factorization, integration. It's a huge skill set, but you take care of it and get to the right result. You know, it definitely pays dividends, especially if you need to get all the frequencies that make up that signal. And it's important that you get it right. So you have to be very painstaking about it. Okay, so this is this term here. Remember, we had the 1 and the plus 7/8 cosine n pi. So now we can put everything together. We finally have all of our Bn, at least the Bn expression, but now we have to get the individual B sub n's. So this is going to be 2 over n pi negative 15 over 8 cosine n pi over 2, which is this from that. And then that's going to be plus 1 plus 7/8 cosine n pi. So if you made it this far, I might even, you know, increase the points, jack up the points to from 300 for this to even 500, because this is a long process, and the question I'm going to give you is going to require your ultimate diligence and high precision. So it's probably going to be worth the most. I'm going to probably make this 500. And the DIY Tesla coil be 300 and the catapult 100. So and you have to get, in order to get 500 test quiz points, this must be exactly correct. So this be very ambitious, but you can do this. You know, it would be worth your time and while to really just do this for the problem I'm going to give you. So the first part, like I said from the very beginning, the other video, is to get an expression for the B sub n's, or we need to get the B sub n's, in order to get the other waveforms that make up the entire green wave that we see at the beginning. So there's individual waves that make up this pulse, or varying peak wave, sound wave that I call there. So like I said, cosine n pi over 2 earlier is going to be 0, but I'm going to get the terms out, and this term here is going to die off. So the next thing I'm going to do is compute all of the coefficients. Because now we have our expression for it. So n is going to be equal to 1, 2, 3, So b sub 1 is we just replace 1 for each of these terms here. So 2 over 1 pi, or just 2 over pi, and this first term goes away, and so all we're left with is 1 and cosine of this is just 1. So basically cosine of pi is -1, so then it's going to be -7/8. And if we carry that out, be 2 over pi times 1/8, and that becomes basically 1 over pi times 1/4, just painstakingly factoring everything out, so it's 1/4. And so basically b sub 1 is 1 over 4 pi. I think I have we're going to just we're going to do the b sub n's. We'll just go all the way up to 8. We'll go for b sub 8. So we got b sub 1, and let's see how this gets put together. So b sub 2 is 2 over 2 pi, or just 1 over pi. Let's not be specific about it. So this is 2 over 2 pi, and then from our term before in these b sub n's here, since that'll be 2, so that's going to be cosine of pi, instead of just pi over 2. So again, let me just go back over this term. We're going to need it. Could have gotten rid of it, but we don't know what the n's are going to be. If the n is definitely going to be 1, then of course that first term can go away. But of course, as we can see, the n's are 1. They can be other integers, 1, 2, 3, all the way up to however many we want. So depending on the integer here, this 15 over 8 term either stays or goes. So 2 over 2 pi. So this is going to be -15/8 cosine of 2 pi over 2, or just cosine of pi, and that just becomes cosine of pi is -1 with the minus sign here, so it's just 15 over 8, and then this is going to be +1, because we're doing everything with respect to this term. +1 plus 7/8, because cosine of 2 pi is going to just be 1, so 1 times 7/8 is 7/8. So this is going to be, so that's 1 over pi. I'm just going to evaluate everything in here. 15 over 8 plus 8 over 8. Excruciatingly explicit. Okay, so that's going to be, remember 2 over 2 pi, that's going to be 1 over pi times 30 over 8, and that equals to 15 over 4 pi. Divide everything by 2, and then I just have it as 1 over 4 pi times 15, because I start noticing this pattern of this 1 over 4 pi business. Okay, so B1 1 over 4 pi. And so B2 is going to be like 15 over 4 pi. So it's 1 over 4 pi is looking like it's going to be possibly a factor for all the B sub n's. And so B3, so it's 2 over 3 pi because n is now equal to 3. Again, we're evaluating all the B sub n's from this formula. So okay, so 2 over 3 pi, and that's going to be negative 15 over 8 cosine of 3 pi over 2, like pi over 2, by pi over the odd multiples of pi are going to be 0 for the cosine function, blah, 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 and which makes cosine an even function, and that's why we're going to use cosine for even sound wave propagations. But that green wave is an odd function. That's why we use a sine, and then the antiderivative of that is the cosine. That's why we have these cosine terms. But anyway, plus 1. I'll just put that 1 here, plus the 1 here, plus 7/8 cosine of 3 pi, because now n is equal to 3. Go to the next one. So this is going to be 2 over 3 pi. So again, this goes to 0 because cosine of 3 pi over 2 is 0. So this is 1 plus or 1 minus 7/8 because odd multiples of just pi is going to be a negative 1. So 1 minus 7/8 becomes 2 over 3 pi times 1/8. And then that becomes basically, you factor all this out. I guess one more time I'll be explicit. So it's 2 over 24 pi. And that's just 1 over 12 pi. And again, that's 1 over 4 pi. 1 over 4 pi, business comes back, times 1/3. So B3 is going to be 1 over 4 pi times 1/3. You start seeing the pattern. It'll be 4, 2 over 4 pi, 1 over 2 pi, minus 15 over 8, cosine of 2 pi, because it's going to be 4 pi over 2, which is 2 pi, plus 1, plus plus 7/8, 1 plus 7/8 cosine of 4 pi. And stretch this out, 2 over 4 pi. This is 1, so it's going to be negative 15 over 8 plus 1, and cosine of 4 pi is 1, and this is plus 7/8. You factor all that out, this is going to be basically negative 15/8 plus 15 over 8, and that's 0. So the B4 coefficient is 0. It doesn't exist. That's the B4. So then B5. See that. This is repetitious. So a high amount of discipline. So there's a high amount of points. Negative 15 over 8 cosine 5 pi over 2 plus 1 plus 7/8 cosine of 5 pi, right? 5 pi becomes 2 over 5 pi. 1. Remember that multiples of pi over 2, odd multiples are 0. So 1 minus 7/8. So goes away. Equals 2 over 5 pi times 1/8, and that equals 2. 1 over 4 pi times 1/5. So you can see a pattern forming with this 1 over 4 pi. So B6, 2 over 6 pi, negative 15 over 8 cosine 3 pi. Okay, plus 1 plus 7/8 cosine of 6 pi. And hopefully by now you can get the pattern. Leave a little bit of the algebra up to you to save time and all of that. But again, this was n equals 6, but 6 pi over 2 is 3 pi. Oh, I guess I'm at this point, so I guess I'd be explicit anyway. 1 over 3 pi becomes 15 over 8. It's minus 1, minus here. Seven-eighths. That equals 2. 1 over 3 pi times 30 over 8. And you do all that, you get 30 over 8. That equals to 15 over 4 pi. 4 pi comes back. And that equals 1/3 times 15 over 4 pi. 1 over 4 pi times 15 over 3, which is just 5. So basically 1 over 4 pi times 5. And that's the B6 term. That's the B6. And then B7, 2 over 7 pi. Remember, 2 over n pi. N is equal to 7 now. And that becomes negative 15 over 8. And because, negative 15 over 8, that's cosine 7 pi over 2 plus 1 plus 7/8. Cosine 7 pi. And that equals to 2 over 7 pi. Again, odd multiples of pi over 2 go away, and this is 1 minus 7/8. 2 over 7 pi times 1 over 8, 1 over 4 pi times 1 over 7. So 1 over 4 pi comes back. So that's B7. Lastly, for B8, 2 over n pi, n is equal to 8. And that's negative 15 over 8, cosine of 4 pi plus 1 plus 7/8 cosine of 8 pi. So that becomes 1 over 4 pi, negative 15 over 8 plus 1 plus 7/8. And back to where we have for B4. Seems like every fourth one is 0. It's negative 15 plus 8. This becomes 15 over 8. So that's it. So at least the first 8 terms of the wave function. Of course, there's n number of terms. It goes to infinity. So we'll just do a first, a few of the first ones. I'll have you do like the first 5. Just want to be explicit. So now we're ready to put everything together. Okay. So that's what happens when you do this Fourier analysis. It's long process, painstaking, but it teaches you discipline and detail and integration. It brings a lot of skill sets together. So be very willing to take your time with this. In grad school, I remember some math majors, I think they were math majors, they were doing a bunch of Fourier series problems, and you just see them on the whiteboard as this girl and this guy, they were just really meticulously writing every step because it requires your discipline. After a while, you can see the patterns. It's easy, but you miss a sign and the whole thing breaks. So, it's very important to take your time, be patient. You can do it by computer, it's cheating, but so by hand, it teaches you a lot. Okay, so anyway, we are now down to the last bit of putting it all together in that original function. We had let's see, let me start up over here. Original function of this pressure as a function of time and the integration from 0 to L. We got all our b sub n's, sine n pi t over L dt. We've now completed the entire integral, and our job was to find the b sub n's, which is the coefficients. And the way that we go about that is to use this function. This b sub n function, this is what we just did. We finally got to the end of it, got all of our b sub n terms. Now we can finally put our b sub n terms into the original p of t function. So let's do that. So again, writing the p of t, pressure is a function of time. This could be a sound wave, a signal from wind or air or something, some kind of signal that's being recorded in terms of pressure, atmospheric pressure, or whatever. And so the integral original was from 0 to L, and we had our b sub n's, sine n pi t over L dt. We did all that. Well, at least we got the b sub n's, and now we can put all the b sub n's into the original function and see what it looks like. So it really is a special form of a series of b sub n terms, and we denote that by this sigma symbol. L equals 0, and it goes all the way up to L, 0 to L, if you will, and then this becomes b sub n and sine n pi t over L. So this is basically the series equivalent of this integral. We're integrating it in terms of dt, and this is basically telling us that the entire pressure wave is a sum of all of these pieces, these b sub n's, and we got all the b sub n's, and I'm going to put them all together. P of t, and remember, all of these b sub n's, except for 4 and 8, because 0, are factors of 1 over 4 pi. Now we take the function, okay, which is sine n pi t over L. And we know that that becomes sine 524, because 1 over L, because L is 1 over 524, so 1 over L is just 524. So it's going to be 524 pi t. And it's going to be divided by 1, because that's the first term in the series. Because, all of these are some form of the b sub n's. So 1 over L is going to be 524 pi times t, and then that becomes divided by 1 for the first term in the series. And another thing too, does this 1 denote to this? It can't, because it's numerator and denominator, but this right here is an understood 1 in front. So we'll see that stretched out. Second term is going to be this is a better way to see that. Okay, I'm just sticking with this first term. If we go back to the first term for b sub n's, or b sub 1 term, we see that b sub 1 is just 1 over 4 pi. So in order to keep its integrity, if you will, this is 1 over 4 pi divided by 1, which is just basically 1 over 4 pi. We'll see how that works, because the second term is going to be written in such a way that it becomes 15. Remember, this one was 15 over 4 pi. Let's see how we can represent that. So this is the first term. To keep the 1 over 4 pi times this, because this is 1 over L, 524, n is 1. You don't have to write it, but then there's pi t. So we're basically writing out the series of b sub n terms here. It's the sigmas, it's the sum of bunch of terms. And so here's plus. Now we can write the 15 if we want, but we have to write the 15 in such a way that it represents the second term in the series. Okay, so therefore the 1 over 4 pi is out here, so we can just say 30 sine 524 pi times t, divide that by 2. 30 over 2 is 15. 15 times 1 over 4 pi is 15 over 4 pi. That's the second b term. B sub 2 is 15, 1 over 4 pi. So we're representing, we're not just writing 15, but we're making the equivalent of 15 in terms of the second term in the series of this pressure function. So something over 1, something over 2, something over 3, all the way up to 8. And we know that 4 and 8 don't work because they're 0. So the next term is going to be the third term in the series. And so we just write sine 524 pi times t. Oh, and let me not Wow, I'll finish writing this out and come back. So sine 524 pi t times 3, because 3 is the third term in this series. So sine 524 pi t times 3 divided by 3. And why are we doing that necessarily? Just to keep things a little less esoteric. Because b sub 3, remember we found b sub 3 to be 1 over 4 pi 1 over 3. That 3 is in this denominator. So that's really the issue. So instead of saying 15, let's say 30 over 2, 1 over 4 pi. I mean, at this point, it's about just keeping consistent with writing the terms in their series or their sequence, whatever term you want to use, it doesn't matter. So this is the first term, second term, third term. You could say 15 because eventually we're going to take this amplitude, which is 15, and we're going to do something with it. But again, 1 over 4 pi is the term to be factored out. This is the first term, 1 over 4 pi times 1 over 1, which is 1 over 4 pi, and 1 over 4 pi in the second term. The second bn term, or b sub 2 was 15, but keep things consistent with their sequencing. This is the second term, so 30 divided by 2, which is 15, times 1 over 4 pi. And then 1/3 times 1 over 4 pi, which we saw is b sub 3. B sub 4 is 0, so we skip that. We'll go to b sub 5, see how we can write the b sub 5 term. It's very simple. We can just say sine blah, 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 divided by 5, 1 over 4 pi. And then likewise with the 6th term, now b sub 6 right here, we can do the 30 over 6 pi type thing. Okay, so let's write the next terms out. So 4 is 0, so we go all the way to 5. This is going to be sine 524 pi t times 5 divided by 5. This is basically 1/5 times 1 over 4 pi, which is what we got for the b sub 5 term. And like I said up here, this is going to be multiplied by 2 because remember, this is sine 524, which is 1 over L, 524, n, where n is equal to 2 pi t, n is equal to 3 pi t, n is equal to 5 pi t, divided by the 5th. Why is this denominator there? It's the 5th term in the series, but moreover, it's 1 over 4 pi times 1/5. And then we do 30 sine 524 pi t times 6 over 6. Because 30 over 6 is 5. 1 over 4 pi times 5, which is the B6 term. Remember, B6 is 5 over 4 pi. This would be 5 over 4 pi. Because this is the big parentheses. And then 7 is our last term because 8 is 0. And so the 7th term times 7 divided by 7. Because look at that, 1 over 7 times 1 over 4 pi. That's b sub 7, b sub 8 is 0. So those are all of our terms. This is the answer. Okay, this is the final result of the p of t function that we saw in the beginning. And let's see, right here. So our job was to integrate this. Okay, first, but the way to do that is they find the b sub n's, which is using this function, which is basically swapping terms. P of t. Okay, P of t is understood to be there, whatever the function is. Then we went through the integration for the B sub n's, got all the B sub n terms, and then we put it back into the original P of t function and showed the wave functions that make up the ultimate wave function. So these, basically what this means, these are the wave functions added together that make up the original guy. Okay, right? Yes, a series of these little wave functions make up the original guy right there. So if you were to zoom in, you could see all these wave functions overlapping that will add up, they will superpose to make up this varying peak sound wave. Other sound waves or other wave forms have different subsidiary or different wave functions that make up those waves. And so it's all a massive harmony of waves making other waves. This is a superposition. This wave right here is a great grand superposition or addition or sum of all of these. And that's what this solution represents. And so what we're going to do lastly is we are going to do a couple of things. We are going to look at the frequencies of these waves, and we're going to look at the intensity of the waves, or basically how loud they sound. And then all of their loudnesses together makes up that peak one wave in the beginning. So everything is super harmonious. This not only has applications to sound, to electric circuits, but also to musical instruments, anything that has a simple harmonic oscillation, a periodic function. And we're just using this Fourier series in terms of sound. We can do it in terms of music. We can do it in terms of anything that has this type of sinusoidal function. We can do it in terms of the hydrogen atom in quantum mechanics. I mean, it's just, you'll find that the wave function itself is a pretty baseline tool to unify everything. So 1 second, pause and come back. Okay, now, so how does each wave sound, or what are the frequencies of all of these different wave functions? These waves are doing their thing. This is a huge sound wave. So each one of these waves has a pitch, has a sound to it that makes up the ultimate sound. We, in the beginning, we listed that the length is 1/524. And if you go back to the original picture, we stated, if you recall, this is the length, and then the period is 1/262. Okay, so the length is 1/2 of a wavelength that we denoted here. A full period is going to be a full wavelength, or twice the length. So if we're just solving for full lambda, not lambda/2, but a full lambda is going to be a full period, which is twice the length. So this is 2L, L, and then add another L for 2L for a full wavelength, which corresponds to a full period. Now, in order to get the frequencies, we understand that frequency is 1/period, if you recall from the simple harmonic motion chapter. So if our period, or since our period is 1/262, then the frequencies this first frequency, if you will, is going to be different frequencies. Why different frequencies? Because all these different wave functions has a pitch. These are individual waves, so they have individual frequencies that we denote by n, where n again is an integer multiple, 1, 2, 3, so on. You can say to some degree that these are quantized, that they're discrete. All these wave functions, they have particular waveforms, they have particular sounds, particular energies, they have particular momenta. So in effect, you can call them quantum, but it would be out of context because these are large waves, large things. So we don't necessarily use it's out of context to use the word quantum, because quantum is small or related to small things. So, but the idea is the same. You can get discrete frequencies, you can get discrete energies, you can get discrete wavelengths, you can get discrete momenta. And you can just, start opening the bag. Start opening the bag and doing all kinds of things that you would normally do in quantum mechanics. Okay, so 1 over 262 is just 262. So get rid of that there, multiply the top and bottom. So the first frequency corresponds to this guy is equal to 262 hertz. That is the pitch of this first wave function. Because remember, this is sound, so we're going to get the frequencies. And so therefore, the second one is the multiple of that. So F2 would be twice the first, so it's going to be 524. And then F3, 786. Okay, 786 hertz, and you get the idea. And so these guys are all in multiples of the first. So this would be called the fundamental frequency. You may have heard of this in terms of music. I was given the guitar reference at the beginning of the other video, and that means that each string has a fundamental, and the fundamental is this first frequency. Now, the guitarist, the musician, instinctively knows that if he places his fingers at different points on the string, he's going to get multiple frequencies. See how that works together for sound in this case, music in another, and even the energy states of the electron in orbit around the hydrogen nucleus. They have different frequencies and different energies. I'm seeing the harmony, the unity of it all. Okay, so F4 is 0 because there was no B sub n, and then F5 is going to be 5 times this, which is 1310, and then F6, 6 times the first is 1572 hertz, and then F7, 1834 hertz. Now, if you're looking on a music chart, you can see that 262 is roughly middle C. That's 261 hertz, 261.50 something. Roughly, that's middle C, and it goes up. So you're hearing pitches of music in this sound wave. You're just now extrapolating all the different frequencies to make up that large tone that coming in. Boo, whatever the sound it can make. It's made up of all these, and F8 is 0. Okay, so those are the frequencies of these guys. So these are the waves, and these are how this is the pitches. This is what they, this is what they sound like. Again, how do we get them? Get the frequencies. Frequency is 1 over period. There's the individual frequencies, so it's N. F1, 262, F2, twice the fundamental. So If you're just multiplying the fundamental by this integer, 2 times 262, 3 times 262, well, 4 doesn't exist, and 5 times 262, 6 times 262, 7 times 262. Again, 4 doesn't exist because there was no b sub n for 4. So it's not there. And f8 equals 0. Okay, I know I'm getting long-winded, but yeah, this is why this is going to be a whole ton of points. So there's the frequencies, and the last bit we're going to get are the intensities. How loud are these pitches, right? So this is the last bit. So intensity, loudness, okay? Because these pitches go high doesn't mean that they're loud. It's different. This is what they sound like. This is the volume. So in order to get the intensities, whoa. I hope I wasn't muted there, but anyway, I had my deal pressed down. Let me see if I was, okay. We have these waveforms. This is what they sound like. These are all the pitches. It's like middle C and so forth. And lastly, what we're going to do is we're going to get the intensity or how loud each pitch is. I don't know if you guys heard that or whatever. Hopefully you did. So intensity is the loudness. So in order to get the intensity, we write down all of the wave numbers that we have. We have 8 of them, and 2 of them don't work, like 4 and 8 don't work. So we're just going to write them down explicitly anyway. These numbers come from the b sub n. So 4, 5, 6, 7, 8. And so the intensity is basically going to be found by looking at the amplitudes. So if you remember from the wave mechanics chapter, how energy is a function of amplitude squared, well, we're going to do here. And that's, relates to intensity. So so the number that we find here is it's going to be proportional to, not exactly equal to. It's proportional to the intensity is a function of the amplitude squared. So let's go back to these guys and let's take a look. Well, the amplitude is going to be the number in front of the sine function. That's all it is. So the b sub n's are made up of the amplitudes plus this factor. So the amplitude is the number in front of the sine function. So this is 1. This will be 15. This will be 1/3. Okay, because remember, we got to take into account the one in the number in the denominator. So this is 1/3, 1/5. This will be 15. No, it's 5. 30 divided by 6. This would be 5. And this is 1/7. So those are the amplitudes. 1 divided by 1, 1, 15, 1/3. But it's going to be the amplitude squared. 1/5, 5, 1/7. So lastly, the intensity will be 1. The second one is 15, but 15 squared. So it's all these different amplitudes. So 15 squared, and then that's for the second guy, for A2 squared. So that'd be 225. So the third one is going to be 1/3 squared, or 1/9. And then 4 doesn't exist. And then 5 is 1/5 squared, or 1/25. And then the sixth one is going to be 5, or 5 squared is 25. And then 1/7 squared is 1/49. So we are done. Okay, so we have all these intensities. Yeah, I'm quite tired. This one, you know, with all the technical difficulties and everything else, it's now 10:30, but labor of love. Okay, so yeah, you get through these videos, you get them all correct. Okay, what, yeah, it's going to be a ton of points. So worth your while. So the intensity, I'll be writing up the problem here in a second for you to get everything. So intensity, loudness is all of the waveforms. Remember, 4 and 8 don't exist because the B sub n's don't exist. So the amplitude for the first function is 1 over 1, or just 1 squared, 1, 30 over 2, 15 squared, 225, 1/9, 1/25, 25, 1/49. So from here, you can see that the second waveform, the pitch at 524 hertz is the loudest. And the not counting this one, and the softest, or the one, is the this 1/49, which is the 7th waveform. Just stuff. Okay, so now for your problem. Okay, for your problem, you have this pulse wave here. So this will be 3, 1, and that. And then -1. Okay. And then this one here, you know, 1 over 262. So this is, you know, 1 over 786. But remember, you can start this problem from the positive domain, you know, I mean, because you know it's going to repeat in the negative, just like we did for the last one. Keep in mind that you're going to have to do the integral over a particular length from its max and min. You know, you can start here at the min, as it were, and then go up to the max. Or yeah, the min would be -3, and you know, -3 here for your problem, and then you start off at 1. You know, from 1 to -3 to cover everything in the positive and negative domain. It's a little bit slightly tougher, but yeah. So with everything, with the length of the videos together, this is like clearly over an hour, probably an hour and a half. You're gonna have to dissect this, get together in a group or whatever, and this will be tremendously worth your while, because you get this exactly right. Ton of points, and you're gonna love it. But must be exactly right. Like nothing inaccurate. I mean, some points will be given for how close you get, and all that stuff. So what are you going to do for this function? Let's see. Okay. It is an odd function. I was talking about odd and even functions. Well, the odd functions, okay. They for the odd functions, they have no reflection accurately across the y-axis, and the odd functions just have like one piece each, one positive, one negative, or it just starts at a positive or starts at a negative. So an even function would be one, and if a function would go across evenly, but no pun intended, really, across the y-axis, and it would come down like this and like that. So it'd be like a mirror image. This one is an odd in the green, even. And so for the odd functions, we are going to use sine because that is an odd function, or an odd pulse wave, or odd function. So again, find your B sub n's using the odd function for the Fourier series, 0 to L. You have to determine what the L is. And then this will be, again, let's say f of t, because this is going to be another pulse wave in time. F of t sine of n pi t over L dt. So you're back, on the video, and remember, recall how you're going to do your B sub n's, how you're going to integrate for all of the coefficients. So this is number one. You got to find your B sub n's. Two, put all the B sub n's in the, I guess, the f of t function, just like we did for the p of t. Once you find your B sub n's, you just put them back in. After you get your f of t, which is like the p of t that we did, before, find your f of t. Then next, you're going to find all the frequencies that make up this sound, and then find all the intensities. And remember, intensity is a function of amplitude squared. So once you get your P of t function, you're going to see all your amplitudes in there that you can get basically from your B sub n's, and allow you to get the intensities. And that is that. Right. Good luck. I will come up with a final figure as to points, because given the enormity of this, originally I know I said 500. Yeah, it's going to be more than that. But okay, talk to you later.